All right. What's going on today? No snow. I think I'm okay with that. I've made peace with a snowless winter.
But that doesn't give us a snow day.
We could just declare a snow day.
I declare snow day.
Okay. Day after tomorrow, snow day. How about that?
Perfect. Friday's off.
All right, so questions. These lights are really interesting. So that's what wall wash does. But if you turn on all the lights and you hit wall wash, that's what it does. It's like a XOR. So you gotta turn the lights off and then XOR 1. All right, any questions? Otherwise, we're just going to keep moving forward. All right. Well, let's go for it. Let's do Oracle of Bacon. So, everybody know the Oracle of Bacon? No? Okay. I usually talk about it in 215. I did this quarter. So, Oracle of Bacon. So, somebody name your favorite actor or actress.
Oh, yeah.
Yeah, what? Oh, good one. I bet it's like a factor of 2 or less.
Well, it's not.
I spelled sponge wrong.
I spelled sponge wrong.
Sponge.
Is it maybe lower?
Oh, sadness. It's not in the database at all.
Maybe he's not really considered an actor. It's a cartoon character.
I beg to differ.
Betty White.
Who?
Betty White.
Betty White. All right, bacon number 2. So Oracle Bacon, right? It tells you how many links you have to go through to get from anybody to Kevin Bacon through movies that they've been in together, and fairly difficult to find a bacon number bigger than 3. There's one person with a bacon number of 7. They were in like a newsreel in the 1800s with one other person, and then that person was in a newsreel with like 3 other people a few years later, and eventually it got Kevin Bacon and 7 links, but usually it's 2 or 3 at the most, and it's crazy. You know, you can go Donald Trump, bacon number 2.
Mike Judge.
Mike Judge,
Wall Street, but he knows sleeps.
bacon number 2. Game over. So this is a graph theory thing. They make the data freely available. So here's their database. It's 164,000 lines, and each line corresponds to one film. So title, cast, director, and so on and so forth. And using this information, you go through the file and you build a graph. And your nodes are people. Okay, so everybody who appears in the cast of a movie becomes a node in your graph. And the links from person to person are anybody that they were in a film with. So you start off and you create all of these links for these people in this first line, and you put links between them, edges, right? And then you go on to the second one, and good movie. And you just keep going, and you end up with a graph of connections. And so here's a hypothetical, and I'm not going to use names. We're just going to have letters. And this is just a random example.
got one with 3.
Going with 3, who was it?
Greg Graff.
Cool. The average bacon number is something like 2.9, so there should be some other ones. Yeah, try to find a 4. Well, still learning about breadth first traversal. So let's suppose this is a graph we have, and our goal is to find how closely any of these nodes are connected to node A. Right, so in the Oracle of Bacon, this would be Kevin Bacon, and we want to know how close node G is, right? And we can find a path 1, 2, 3 edges like that. We can find a path 3 edges here. We can find a path 3 edges here. We can find longer paths from G. We could go 1, 2, 2, 3, 4, right? But if you're looking for a shortest path, that's a classic algorithm. And so shortest path from a fixed node, that's basically a breadth first search. The same thing we were doing in PA4 with tree traversal. And here's the basic idea. If we start with node A, and we look at every node that's directly connected to it, we know the distance from any of those nodes to A is exactly 1, right? The shortest distance. So B, shortest distance to A is 1, C, shortest distance is 1, and so on. If we then find any node directly connected to one of those nodes that has a distance 1, we know the shortest distance to that node is going to be 2. Because the best we can do is get to one of these nodes with a distance of 1. So what we're doing is basically sort of farming out from one point. We take one step, and after one step we're going to get to B, C, and D. If we take a second step, we're going to get to E, and F, and H, and J. If we take a third step, we'll get to G by multiple ways, and so on. And so as soon as you reach a node, you have found a shortest path to that node. Does that make sense? And that's really all that breadth first search is doing. It's slowly moving sideways as opposed to depth first search. Now, if we did depth first search like we do with trees, when we do in-order traversal, we might start at A and then go to B and then E and then G and then I and then K. And then we'd back up to G and we go down to J. And then we back up to G again and we'd go over to H and so on. We try to move as far as possible before we start going sideways. Breadth first is the opposite. We try to stay at a high level and explore everything at that depth before we move deeper. And so we can code this exactly like we did in PA4 by using a queue. So we make a queue, and I'll draw the head over here on the left. And we seed the whole process by inserting our initial node A. And I'm also going to store the distance between this node and A, which is 0. And I'm going to store the path to this node, which is just A. So that's not very interesting. So what's our breadth first algorithm? What are the 2 steps of it from PA4? Remove the head and insert the children, right? Okay, so we're going to remove A. And so we know A has a distance of 0, and we get there by going through A. Now we want to insert all the immediate children of A into the queue. Doesn't matter what order we do these in, so I'm just going to go from top to bottom. So here's a child, B. So we're going to insert B, and we're going to take the length of A, right, which we removed, and we're going to add 1 to it. So this is going to have a distance of 1, and the path is going to be whatever the path was that we used to get to A, followed by B. And I'm also going to do something else here which is different. I'm going to circle a node once we've explored it. Because with trees, we just know we're moving down and we're never going to come back to a node we already saw, because there's no cycles in trees. With graphs, there can be cycles. So when I visit a child, I'm only going to put it into our queue if we haven't already circled it. Okay, that's just to prevent loops. So there's another bit in here that corresponds to whether it's been visited. So we find node C, we're going to circle that. We're going to put that in our queue. Its distance is going to be the distance we removed, 0 plus 1 is 1, and the path will be the path we removed, A, plus the node itself. And then there's another child of A, which is D, so we'll circle that, we'll put that in, distance is 1, path is AD. And that's it for the children of A. Okay, so now we're going to remove the head of the queue. So this is B, distance of 1, path is AB. Bless you. And we're going to insert the children of B. Well, here's one child, J. So we'll put J in, we'll take the last distance we removed, 1, and increment it, and we'll take the last path we removed, AB, and we'll add J. Here's another child of B. So we'll put in E with a 2 and ABE. And here's another child of B. So we'll put in F, distance 2, path ABF. Any other children of B that we haven't visited yet? Right, so we'd also find that C is a child, but that's got our bit set saying we've been there. We'd find that A is a child, but that's got our bit set. So we're done. So remove the head of the queue. And then add the children of C. Well, visited, visited, visited. Here's the only new one. So there's an H, distance of 2, path of ACH. Got the idea? So it's the same algorithm that we did for trees. Remove D. And there's no children that we haven't visited that are adjacent to D, so we don't insert anything. So now we go ahead and remove J. These are temporaries. Remove J, ABJ, and add its children. So children of J, well, there's a child, G. So G, distance 2 plus 1 is 3. ABJG. And G has a child, I. Distance 3. Sorry, we removed J. So that's not visited. Any other children of J? K. So add that, ABJK. And that's it for children of J. So remove E2. And there's no children. Remove F2. There's no children. H2, nothing unvisited. G3. And here J has a child A. So that's a distance 4, and it's AB, JG, I. And then remove K. And remove I. Yeah. And then try to remove from the queue, and there's nothing left in the queue, and we're done. And what we've been removing from the queue is the shortest distance and a path to get that shortest distance from A to each node. So shortest distance to G is 3, and one way to get there is go from A to B to J over to G. So if you have a particular node you're looking for the distance from, you just do this until you pull that node out of the queue. If you want the distance to every node, you can just keep going until the queue is empty, and then you've visited everything that's connected to A, directly or indirectly. So how do you code this? Well, you could make each node a linked list of pointers to other nodes, because we don't know ahead of time how many links there might be to a particular node. So a linked list we can grow as big as we want, as opposed to an array. So what might your struct node look like? Let's call this a graph node. So what do we need to keep track of in a graph node to do what we just did on paper? Say again? Okay, so let's have a car star name. What else? Okay, so distance, good. So that can be an int. Say again? Okay, so let's have a visited flag. And then you said a list of the children. So let's make that a linked list. So I'll call that a struct list, or we can type def it. And if we're going to put these things into a queue, maybe we also want something like a car star path to save this information about ABE, ABF, and so on. Maybe not, but memory's cheap. Anything else we need in there? That's probably good. So what does our linked list of pointers to children look like? What kind of data are we going to store in this list? Say again? Yeah, we just need to, I mean, if we're doing a tree, we have pointers to the left and right child. If we're doing a graph, we need pointers to, you know, child 1, child 2, child 3, whatever the collection of child nodes are. So we're going to make that as a linked list. So our data is a struct G node. So here's a child. And then a struct list star next. So what does our list look like? Right, it's a linked list of these struct lists where the data piece points to a G node and the next piece points to another node in our linked list. And then these G nodes just capture this information. They don't really travel down. And so node A, its linked list would be something like, and I don't know if we want a sentinel or not. We'll put in a sentinel just because we always do. So this could point to A. Sorry, this could point to B. This could point to C. This could point to D. This would be null. So there's the linked list corresponding to node A's children. And when we're going through our breadth first search and we say, let's find all the children that we haven't visited yet, what do? We start at the beginning of the linked list. We look at the first node. We take the data portion. That gives us a G node. We go into that G node and we say, is the visited flag set? And if it's not, we set that to a 1. We look at the distance, we update it according to the distance we popped out of the queue, and we push it into the queue, and so on and so forth. So this is what you do in computer science, right? This is kind of the heart of most programming that you're going to end up doing, is basically designing data structures and then implementing them. And you can do whatever you want with these, right? After you've got experience with different basic types of data structures, you can start putting them together. We could make, if we were really worried about efficiency and we were searching for children with particular characteristics, instead of making our children a linked list, we might make it a tree. We might make it an AVL tree or a red-black tree if we were really crazy. There's really no restrictions here, right? It's totally up to you. That's part of what you get to do as a coder. I was chatting with a friend last night. We were undergrads together, and he implemented one of the first Unix systems available on a system called a VAX. This was back in the 70s, early 80s, and he was building the whole network stack for the operating system. And so we were talking about AVL trees. This is how this came up. He coded an AVL tree inside the heart of this stuff to do address resolution, just because it was fast, and having a self-balancing tree, it was just a efficient implementation of a way to store this information and then retrieve it quickly. And you know, same thing you're doing in your programming assignments. Well, that's what he was doing, but you know, he was writing code that was being used by thousands of people and stuff like that. So I mean, this stuff is real, and it's your tools that you can take and put together and use to create like other things, right? So it's not just going to be an academic exercise. You're going to be doing this stuff throughout your careers. So, and I think it's a lot of fun. I mean, it's like Tinker Toys, basically. All right, let's keep going with trees. Oh, and I'm going to stop talking about 10 minutes early, and I'm going to leave, and the reason is I want you to make sure that you respond to the thing on Canvas that asks you to do an evaluation on me. Has everybody seen that? How many people have done it already? Oh, most people. Okay, good. So if you have not done that, and or if you have not done it for 2:15 yet, I'm going to give you like 10 minutes at the end. I'll take off at 10:40. And you can either, you know, use your laptops here, or if you don't have equipment, go to the collaboratorium and just hop onto Canvas and take care of that. Because the closer we get to 100% participation, the better. And it's pretty important. So they usually encourage me to give people time during class to make sure they get that done. So you get 10 minutes today. Or you go outside because it's sunny and do it outside. All right, this is assuming I can remember.
I'll stop you.
Okay, thank you, thank you. Because I don't have a watch to set. Let's talk about Huffman coding. So suppose you have a bunch of text, okay, just, you know, ASCII characters, and you want to store that text in a file. What do? We use an Ascii table. We find the 8-bit code associated with each letter, and we write that into our file, one after another, and then when we go through our file, we can look at it in 8-bit chunks and see what the set of letters are that are stored. That's straight binary encoding, and if you just kind of go into a Unix shell, right? You make a text file. And you look at the binary contents of that file. I'm looking at it in hex here, right? There's a hex 41. That's the letter A. 42 is B. 43 is C. 44 is D. 47 is G. And 0A is a new line, right? So it's just putting those bits down one after another. I don't think octal dump does binary. Yeah, that's just bytes. And so if you have n characters, it's going to take 8 times n bits, or n bytes, to store the contents of your file. So we made haha, which had 7 letters and a new line at the end. And if we look at its size, it tells us it's 8 bytes. So what if we want to use less storage? What if we want to store 1,000,000 characters, but we don't want to take 1,000,000 bytes to do it? And so this is the idea of compression. And there's a lot of different compression schemes, and they're based on different characteristics of what you're trying to compress. One compression scheme that you'll see a lot is something that looks for repetitions of a character. And if it finds the letter Z 20 times, instead of storing Z, 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 Z 20 times, it'll store the letter Z once, followed by the number 20, with some kind of indicator saying that this letter is repeated. So maybe it'll use a special character to say we've got a repeat coming up, and then it'll show the character, and then it'll say how many times. And in 3 bytes, you could store, 100 Z's instead of 100 bytes. So you'll see things like that used sometimes. That's called run length encoding. Any guesses where that might be a useful compression scheme? What kinds of data might have long repetitions of the same thing?
Cashier's registers.
Possibly.
Images?
Images, right? So take a look around here. I look at the back there and I see this big long bar that's pretty much the same color all the way across. There's a little break everywhere the panel hits. And the whiteboard is just, pretty much the same color across each of those individual panels. And if I take an image and I code it by running horizontally and slowly moving down, I'm going to see a lot of repeats of the same pixel information, usually. If I tilt it a little, it's a different story. But a lot of things that we observe tend to have this pattern. And so image compression schemes often use run length encoding. If we're coding text, there's certain combinations of letters that are going to occur frequently. For example, a T followed by an H followed by an E is going to occur pretty often. And it occurs often enough that it might be worth coming up with a slightly shorter way to code that particular combination of 3 bytes. And any time that we come up with a different coding, it's going to cost us a little bit, but it may be that we can gain more than we lose by introducing this special coding, and we end up compressing our files. And so that's gzip, haha. So haha went from 8 bytes to 33 bytes. Not a very good compression scheme, right? Because we can't just make things smaller, right? We got to somehow let the system know that what it's looking at has some sort of coding associated with it. But if I take something large, all right, so now I've got 105,000 characters inside haha. Let's zip that up. All right, that came down to only 263 bytes. Huge savings. Why? Because I had the same line repeated thousands of times. That's pretty easy to encode. You're going to see this pattern of characters, and it's going to be repeated a gazillion times, right? And it doesn't take much space. So 7,000 lines, and it's all the same stuff. On the other hand, here's a file, 133,000 bytes. This is a binary file, right? It's actually a copy of the LS program. So if I zip that, that only came down to about 60%, 50% of the original size. Right, because it doesn't have a whole lot of redundancy inside. It's binary, right? And it's not clear that there's some English text. It's not clear that there's a particular collection of sequences that occur frequently. But there's different ways that you can compress binary files, right? So there's lots of different schemes. So Huffman Coding is really good for working with things like written text, okay, stuff that corresponds to language. And it compresses based on the frequency with which certain characters appear. So if you look at text written in English, what's the most common letter? Letter E. And least common is, I don't know, it's probably Z or something. Something we don't bump into a lot. So here's the idea. Suppose that instead of using 8 bits for every single character, we come up with a different coding that uses fewer bits for the characters that are more frequent. And then the characters that only pop up once in a while, maybe those will take 10 or 12 bits. But we don't care because they only occur once in a blue moon. But the letter E, if we could represent the letter E with only 5 bits, that's a potentially big savings. If we represented the letter E with only a single bit, that would be a huge savings. Because if E pops up 8% of the time, right, 8% of the time we're using 1/8 as much storage. So Huffman coding is a variable length code. It uses different lengths of bits for each character. And so let me give you an example of the results of this, and then we'll talk about how we actually come up with this coding. So suppose we have the following frequency information. I also did this at breakfast yesterday, so A, B, C, D, E, F, G. And these are sort of dimensionless frequency numbers. Oh, oops. There we go. These are dimensionless frequency numbers. It's just higher number means that this is more frequent, and they're relative to each other. So we got a simplified alphabet with only 7 letters, and E is the most frequent letter, followed by A, followed by B and F, who have similar frequencies. C and G have slightly lower frequencies, and D is the least frequent letter. So we have 7 letters. We could use 3 bits to code this information. And that would give us unique codings for each of these, plus we'd have space left over for another one. But let me show you a different coding. Well, let me just put this down here. So here's the coding that a Huffman algorithm might come up with. So A is going to be 0, 0. B is going to be 1, 1, 0. C is going to be 0, 1, 0, 0. D is 0, 1, 0, 1. E is 1, 0. F is 111, and G is 011. Is this disturbing at all?
Yeah.
Good. All right. So it's got the frequency-based characteristics. The letter E only takes 2 bits to store, right? And if that occurs 6 times more frequently than the letter D, which takes twice as many bits, that's a win, right? The letter A, which is almost as frequent as E, also only takes 2 bits. So the question you're probably asking is, can we actually decode this? Right? If we see a pattern of 1s and 0s, can we turn it back in? Because how do you know how many bits you're looking at, right? Should I look at the first 2 bits and decode it as a 2-bit letter, or should I look at the first 3 bits and decode it as a 3-bit letter? And it turns out that it's unambiguous. And here's the way this works. Suppose we see, well, let me just write something out for you here. So. Suppose this is our compressed file, right? So we're looking for some letter that begins with a 1. That could be a B, or it could be an E, or it could be an F. Okay, look at your second bit, it's a 1, so we're looking for some code that begins with a 1, 1. That could be a B or an F. Go on to our third bit, and there's a 1, 1, 0. We're looking for something that begins with a 1, 1, 0. That's got to be a B. So these 3 bits correspond to B. And now we've got a 0, and it could be any of these things that start with a 0. Go to your second bit. Looking for something that begins with a 0, 0. There's only 1, and that's the letter A. And here's a 0. That could be multiple things. Here's a 1. That could be multiple things. Here's a 0. That could be multiple things. When we get to the fourth 0, 0, 1, 0, 0, that's got to be a C. And it's guaranteed, if you come up with this coding correctly, which is what the Huffman coding algorithm does, that when you write out any collection of coded characters, you can always reverse that coding, right? And the only trick is, right, if you start, you're going to start with a 0 or a 1. If 0, 0 is going to be a code for A, there can't be any other code that begins with a 0, 0. So any other code that begins with a 0 has to be followed by a 1. 0, 1, 0, 1. Here's a coding 1, 0. Any other code that begins with 1 has to end with something other than 0. Right? So there's a 1, 1. There's a 1, 1. This can be the only code that starts with a 1, 0. So we'll go through how we come up with this coding based on a frequency table. And the procedure will guarantee this ability to reverse the map, and it will also give us a coding that's efficient in terms of more frequent things take fewer bits, and vice versa.
But this type of compression is limited explicitly by the zip curve, right? Most of the time.
By the what?
Zip curve?
Yeah. For whatever it is that you're coding.
Yeah.
Right? So if you're not coding English, you can still come up with a frequency.
But that's like the limiting factor.
Yeah.
Is there anything that gets past that? Or?
No, probably.
Okay.
I mean, like run length encoding is bounded by the nature of your data, right? But this is a test thing is a good example of that, from 100,000 down to like 50 or whatever that was.
Yeah.
All right, so I'm going to take off, and please, if you